we can start recording. Okay, so in our quest to finish chapters 1 through 8 before the semester is over, today we will hit the milestone of finishing chapter 3. Mercifully, a nice short chapter. And then you'll be able to hopefully do the 4 problems that I put out for this chapter that are listed on the site. Okay, so auxiliary classification transformation of second order linear PDEs. We covered hyperbolic last time, and we'll deal with parabolic and elliptic today. But there's one last comment I want to make that I didn't get to last time about a hyperbolic case. And it's actually sort of a short foreshadowing of what I'm going to cover when I get into the next chapter. Starting on Wednesday. So recall that the canonical form is u p eta plus lower order terms is equal to whatever you had for g on the right side. So the whole reason for transformation is to get a PDE that's easier to solve. Now, in the special case where all you have is this principal part, so second derivative with respect to c and then eta is equal to 0, that is particularly easy to solve because all you have to do is integrate this twice. So you integrate this once, like with respect to c, and you get, so if you integrate with respect to c, that cancels out the derivative with respect to c, and you're left with du d eta is equal to some arbitrary function of eta, which I'll call g of eta. So that's basically your constant of integration, if you will. And then you integrate again with respect to eta, and you get u on the left side, and then this gets integrated with respect to eta also to give you some function capital G that's the antiderivative of little g. But you add on to that your plus c again, which this time is going to be a function of c because you were integrating with respect to eta. Okay, so this right here is your general solution. And then you would fill in what big F and big G are using initial conditions. This is actually how we're going to solve the most important hyperbolic PDE, the wave equation, when we start chapter 4. So now, if you have lower order terms here, then it's still going to be something more difficult to solve. Like maybe you can try reducing it to some sort of ODE. And I'm actually, one of the later examples I'm going to do in the parabolic case will give you an idea of how you might be able to do that. But I just want to focus on this special case, one that's particularly easy to handle, but it's also significant for the wave equation. Okay. All right. So now we can go ahead and move on to the parabolic case. Okay. Whoops. Okay. So to refresh your memory, the general second order PDE we're dealing with is AUXX plus 2B UXY plus CUYY plus DUX plus EUY plus FU equals G. And it is parabolic if its discriminant b squared minus AC, again I'm getting a quadratic formula wrong here intentionally, is 0. Okay. So what we do is our canonical form in this case is you could pick either one, but this is what I'm going with. Plus some lower order operator. So this is the only second derivative term is equal to, well I have in the notes G bar, but G bar is equal to G. Okay. Now, so what we can do is, if our transformation from xy to c eta is non-singular, that means that our new discriminant, which is b bar squared minus a bar c bar, is also going to be 0. Now, the way we're setting this up, in our canonical form, we don't have a xc eta term. So, there is no going to be, there's not going to be any b bar. So we impose b bar equal to 0. And then, well, actually, what we can do is, I'm not going to impose that. I'm going to require that a bar will be non-zero. In fact, what I prefer is for it to be a constant. That'd be ideal. And we're going to force c bar to be 0. So that's how we're actually going to come up with this transformation. We're going to find xc and eta, those new coordinates, that will cause c bar to be 0. Now, if we keep that in mind here, by making c bar equal to 0, this whole term is 0. So that has the effect of forcing b bar to also be 0. So that means that in terms of trying to figure out what transformation will work, we only have to focus on c. B will take care of itself because of the parabolicity of the equation. All right. Okay, so we don't need to set some equation like b bar is equal to 0. We can just do that for c. Okay, so to make c bar 0, our formula for c bar, now this is from last time. Last time I wrote out formulas for the new coefficients in terms of the old. So I'll just repeat the one for c bar here. It's a eta x squared plus 2b eta x eta y plus c eta y squared. We want that to be 0. Now, I'm going to mess with this algebraically to get a simpler equation to work with. First, I'm going to pull out 1 over a, but also, because b squared minus ac is 0, that allows me to write c as b squared over a. So I can just go ahead and make that substitution in there. So that means if I pull out a 1 over a, then what am I going to have? Well, to compensate for the 1 over a, I need to multiply this by a, so that gives me a squared, a to x squared. I need to multiply this by a as well, 2ab, a to x, a to y. And then, because I have a 1 over a already been factoring out, what's left is going to be a b squared, a to y squared, and that's 0.
So then you have a quantity squared.
Yeah, I have a perfect square, so now I can factor that. So now I have 1 over a, and then I have a to x plus b, a to y, quantity squared is 0. So now I just need this. A to x, a to x plus b, a to y to be 0. Okay. Now, what can I do with that? Well, we're going to, as in the hyperbolic case, we're focusing on curves where eta is constant, so our coordinate curves, at least for eta. And what we have is d eta, which would be a to x dx plus a to y dy. Well, eta is not changing. Eta is constant, therefore all this is 0. So I have dy dx is equal to minus a to x over a to y, just by rearranging that. But I have a relationship between a to x and a to y down here also. So I can take this and rearrange this to get an expression for a to x over a to y. So what do I have for a to x over a to y coming from here? Keep in mind that that whole expression inside is going to be 0.
Negative b over a.
What?
I'll wait till.
Negative b over a.
Yes, it is minus b over a. What?
I have a question.
Yeah.
Back here at the bottom, when you substituted in for c, go over.
Yeah.
You substituted in the b squared over a, and then you factored out a 1 over a.
Yeah, from
In
everything.
the first step, then how do you have a squared left?
Oh, because there was an a. Because I'm pulling out a 1 over a, I have to compensate that by multiplying by a.
Oh, never mind. I was pulling
And that
out.
too.
In my brain, I was pulling out an a. Never mind.
Okay. Okay. So yeah, setting this equal to 0 and then isolating a to x over a to y gives you minus b over a. So now I can use that up here and get b over a. So now I solve this for dy dx. So b and a are known; those were coefficients of my original PDE. So, but now I have these are functions of x and y because this is linear. So now this becomes an ODE where x is the independent variable and y is the dependent variable. And what that gives me is the eta, so I'm going to solve this by integration somehow, and eta is a constant of integration when you solve this. And I'm going to demonstrate all this shortly in an example. So this gives you a formula for eta in terms of x and y. All right. Now the thing is, in the hyperbolic case, we had both xc and eta to solve for. So we had two ODEs to solve that were independent of each other, and we got formulas for xc and formulas for eta. Here, we only have a formula for eta. What about xc? We don't have any ODE specifying xc. And the reason for that is you could actually choose xc. So you choose your other variable as simple as you like, preferably, so that the Jacobian of a coordinate change, which would be cx eta y minus cy eta x, is non-zero. That way it's a non-singular change of coordinates. For instance, what you could do is just choose xc to be a function of maybe only x or only y. That way, one of these terms will be 0, and you can just ensure that the other term is non-zero. So that would be a most likely course of action there. So then you have your change of coordinates that will give you this canonical form, because you're making c bar equals 0, which forces b bar to be 0 by parabolicity. And then what you can do is take your resulting equation. You're going to have some a bar, but you can divide through by that if you want, so that you have your new PDE in this much simpler form. Okay. So any questions about how we construct the change of variables, like c and eta, for a parabolic equation before I step through an example of that?
So the fact that you can make a bar equals non-zero, force c bar equals 0, like, is there any like constraint to that, or we can do?
Well, yeah, that's something you can always do.
Okay.
Yeah. Because you're going to have something non-zero here anyway, because otherwise you wouldn't have had a second-order PDE in the first place. But somehow this whole expression still turns out to be 0. So then you can decide what's going to be non-zero. And
Right, because A, B, and C are the principal part, right?
yeah,
So if they were 0, it would just be a first order.
right,
Oh,
yeah.
Okay, right.
Yeah.
Okay.
And the thing is, because a lot of this comes from what's your canonical form you're aiming for. Do you want this, or do you want u eta eta? Yeah. And the thing is, really you can only choose this or u eta eta for your canonical form. If you're going to have a mixed partial derivative, you're going to have this, and then you also have that both of these non-zero also. It's not really much of a canonical form at all. It's like you haven't changed anything. Okay. And if you're going to have exceed eta terms both, that's what you'd have normally in the elliptic equation. Okay. So in this example, I'm going to take a complicated second order PDE that's parabolic, transform it to canonical form, and then we'll solve the canonical form. Okay. Okay, so our parabolic PDE is x squared uxx minus 2xy uxy plus y squared uyy. Then we have plus xux plus yuy is 0. And we're assuming that x is positive. You can have some PDEs like this one which could vary type throughout the domain. In fact, one of the homework problems has a PDE that's either parabolic, hyperbolic, or elliptic, depending on what part of the domain you're in. But at least this way, we only have one type. So our discriminant is b squared minus ac. So b is just the xy, or minus xy. leave out to 2. And then A is x squared, and C is y squared. So once you work all that out, sure enough, you get 0. So this is parabolic. Okay. So now what you're going to do is to get your formula for eta, you can just jump directly to the ODE I gave last time. So all that gobbledygook I did before was just to show you how to get to this. So we just have dy dx is b over a. So b in this case is minus xy over a, which is x squared. So we just get minus y over x. Now, this is a separable ODE. So if I treat this like any other separable ODE, what we get is 1 over y dy equals minus 1 over x dx. So then we go ahead and integrate both sides, and we have natural log of y is equal to y minus natural log of x, but that's the same as natural log of 1 over x plus a constant. Okay. Actually, no, I should not have done that. And it's not wrong, but it becomes inconvenient. Because then what I really want to do is move this term to the other side. So we have natural log of xy is equal to a constant. Because, why does that work?
Because of the condensing of parameter.
That's just rule.
Yeah, the property of logs. Yeah, a sum of logs is a log of a product. That's what I did there. So now you exponentiate both sides, and you get, and I'm using eta for my constant of integration. So I have eta is equal to xy. So that works as a part of my coordinate transformation. Okay. Now, I need to choose something for c to make sure I have a non-singular coordinate change. I'll just choose c equal to x. Now, to make sure that this works, my Jacobian is cx eta y minus eta x cy. So let's see, cx is 1, eta y is x, eta x is y, and cy, is 0. So I worked all that out, and I get x, which in this case is positive, because we're restricting to that part of the domain. So we do have a non-singular coordinate change. So this transformation works. So then what we do is use these to come up with our new PDE. Now, this requires all the formulas that I gave last time for A bar, B bar, C bar, D bar, E bar, F bar, and G bar. All of those, which I won't repeat here. But once you apply all that with these, the partial derivatives that come from these, your new PDE is very simple. So it's U C plus 1 over C 0. Okay. So our principal part has just this one term, and then we have this lower order part also. Okay. So now we can try solving this in the new variables, C, and then use these coordinate changes to go back and express the solution in terms of x and y. Now, here's what you can do to solve this. Because you can really think of this as a second order ODE. But because each of these terms is a derivative, you can actually reduce it to a first order ODE. So I'm going to let v equal to u to xc, and now we have vxc plus 1 over xc v is 0. So now it's a first order ODE. Hold on, I need to make a correction in my notes. Okay, I'll tell you what that is when I get to that point. Yeah, in the notes I have W here, but I'll stick with V. All right, now if I rearrange this,
Separation of variables.
well, actually, well, you could treat it. You could treat it as a separable equation, but when it's of this simple a form, where you have derivative equals your function times some coefficient, the easiest way to handle that is just by integration. You get e to the integral of this. Tell my squigglies are deteriorating. Okay. Now, I do need an arbitrary constant here, but it's not really a constant. It depends on eta. Don't forget there's still eta in the picture, even though it doesn't explicitly appear in the ODE. So I can have some arbitrary function which I'll call f of eta.
So are you
Okay.
technically integrating both sides or not? No, yes. Kind of.
You can't really think of it as integrating both sides when it's written like this. What you can do is think of this as dv, if I divide this, dv over v is minus 1 over xc dxc.
So it's more of just a rule.
Well, here's what happens. You integrate this, you're going to get natural log of v, and you integrate this, and you get the integral of that. And then you take the exponential of both
I'm
sides.
sorry I asked.
Okay. All right. Okay. Now, e to the minus integral of 1 over xc. Well, we could work out that integral. What is that integral?
Negative natural log of c.
Yeah, so this is
You negative c. Afterwards.
so you get that when you integrate, but then how does that simplify?
It's just
Negative
the squiggly. Negative squiggly.
1 over c.
1 over, it's squiggly to the
Whoops.
minus
Yeah,
1.
Whoops.
Yeah, because I can move this up here so the e and the log cancel out and you get
Yeah, whoops.
f beta.
Over squiggly.
Okay, so that is my v. Any questions about that? Yes.
I have a question that is a few steps back.
Okay.
Could you explain how you got eta equals xy from the way up there?
Oh,
Yeah.
okay, because, so after I exponentiate both sides, I have xy equals a constant,
Equals eta. Oh, okay.
and my constant is eta.
Okay.
Okay. I could have called that eta, but then you might as well get into a more convenient
Right.
form.
Okay.
So you multiply by a constant, in this case f of eta.
Yes.
Because it's
Because that actually comes from here because you integrate both sides. When you do that, you get a, well, I'll call as g of eta, and then you exponentiate, and when you exponentiate the sum, you get a product. Yeah, so you can think of f of eta as being e to the g of eta. Okay. All right. So now we have v. But that's not what we want. We want u. Well, u is just the integral of v with respect to c. And once we get that, we're integrating with respect to c, so f eta is like a constant. So I have f of eta natural log of xc, but we need to add on another term here, so I'll just call it g of eta. Okay, and then I can get my final solution, u of x and y. I put this back in the original variable, so that's f of xy, natural log of x, plus g of x times y. Okay, so that's just putting it back in the original variable. So that's something that can be confirmed, that this, for any choice of f and g, solves the original PDE. But thankfully we didn't have to try to solve that directly, because that would have been a real pain. Okay. So questions about that adventure?
That's a U, right? Is that
Yeah, sorry. Yeah, this is
Oh,
a
okay.
U. Okay. And this is du dxc. Alright. How are we doing on time here? Oh, okay. Alright. So that's parabolic equations. Now, what about elliptic? Okay. All right, so what happens in this case is where b squared minus ac is negative, which for a quadratic formula is a case of complex roots, and that actually is going to play a role here. So the canonical form we want is u c c plus u eta eta. So this is a Laplacian of u plus some lower order differential operator is equal to whatever your right hand side was. Okay, so basically all elliptic equations relates to just well, essentially the Laplacian plus lower order things. Okay, so what that means is we want a bar and c bar to equal one another, so then we can just divide through them. And then b bar.
Excuse me, we just did the parabolic, right? Parabolic.
Yes.
Okay.
Okay. So in order to enforce that, if we go back to, again from last time, formulas for all three of these coefficients, I'm going to, for my first equation, I'm just going to say I want a bar minus c bar to equal 0. So I'll put those two expressions for a bar and c bar together on the left side. So we get A, and then the cx squared is from A bar, and then minus eta x squared is from C bar. And then I have similar terms. Okay, so I have cx, cy minus eta x, eta y, plus c, cy squared minus eta y squared. And all that must be 0. And then I have a second equation for B bar. So that's going to be A cx eta x plus B cx eta y plus cy eta x plus C cy eta y. And that has to be 0. Okay. Now, I'm trying to solve this for cx, eta x, cy, eta y. And as you can imagine, that's going to be kind of a pain. So we're not going to do that. Instead, we're going to make a coordinate change on top of our coordinate change that we still don't know what it is yet. So I'm going to let new variable phi equal c plus I eta. So yes, we're actually going to move into the complex plane here. So what that would mean is d phi dx is going to be cx plus I eta x. And then similarly for phi y. So now if I were to square this, phi x squared, so I'll just write out phi y also, because we're going to need that. Okay. So now I go ahead and square this. So doing multiplication in complex numbers. So I'm going to get cx squared minus eta x squared plus 2I cx eta x. And then I'm going to have a similar expression for phi y squared. So that's going to be cy squared minus eta y squared plus 2I cy eta y. Okay. And then I also need to product phi x times phi y. So I multiply the real parts, so that's cx, cy, minus product of imaginary parts, eta x, eta y, plus I times cross terms, so I get cx, cy plus, cx eta y plus eta x cy. Alright. Now, fine, but how does that help me? What I can do then is try to take these equations and rewrite them in terms of these products, phi x squared, phi y squared, and phi x dy. Because notice, take a look at phi x squared. I have cx squared minus eta x squared. I have that same thing up here, multiplied by a. And then I have this part, cx eta x. I have that here in the other equation, also multiplying a. So here's what I can do. I can take these two equations and linearly combine them. So I have a bar minus c bar plus 2I b bar all has to equal 0 because this is 0 individually and that also is 0 individually. But then if I were to take these two expressions and put them in the same linear combination, then here's what I'm going to get. I'm going to get A times this plus 2I times this. That's exactly Vx squared. So all my 8 terms condense to that. Then I move to the B terms. I have Cx, Cy minus eta x, eta y right here. And then I have this, my imaginary part, right here. So I'm going to have plus 2b Vx, Vy. And then, just like I did for the A terms, if I look at the C terms, I could get that to, I could recognize Vy squared. So plus C Vy squared is 0. So now I have one much simpler equation to solve. And in fact, we've seen this equation before. In the hyperbolic case, where instead of Vx or Vy, we had either Cx, Cy, or eta x and eta y. But generally we can proceed like we did before, and what we get is, so this is taking the page from a hyperbolic case playbook. What we get for dy dx, what we got before was minus cx over cy, or minus eta x over eta y. So now we're going to get, instead, b plus or minus I square root of ac minus b squared all over a. All right. And the way you can see that is, okay. Actually, yeah, I'm going to do it on this board. Even though I've already done something similar for the hyperbolic case, we'll see where it comes from. Okay, so from the quadratic equation I have, if I divide through by Py squared, then I get a quadratic equation in the ratio Vx over Vy. So I get Vx over Vy is equal to okay. Now, but the thing is, I have d phi is, which is 0, is Vx dx plus Vy dy. So you saw something similar in the parabolic and hyperbolic case, that dy dx is equal to minus Vx over Vy. So then I just take minus that, and that's how I get b plus or minus. And then I factor a square root of minus 1 out of that, which is how the I appears. And notice I've changed the discriminant around, ac minus b squared over a. So we can see real and imaginary parts. Okay. So now what we can do is we can solve this ODE. And because of a plus and minus, we're going to have two solutions, which I'll call phi1 and phi2. So I've only described one variable phi, but because there's a quadratic formula, we're going to get two solutions. But these are complex. And because A, B, and C are all real, how are these solutions, these are complex, but how do they relate to one another?
The real part.
What?
Like the real parts are the same.
Well, yeah, but we can actually make a stronger statement than that. For instance,
They're complex conjugate.
complex conjugates. Yeah. So phi1 is phi2 complex conjugate. So what we can do is we can just let C equal the real part of phi1 and eta equal the imaginary part of phi1. It doesn't matter which we designate to be phi1 and which is phi2. That's only going to change the sign of eta anyway. Okay. So now we have formulas for C and eta. And we can now we can apply the change of variables to our original PDE of the same formulas for A bar, B bar, C bar, and so on. And then we get our canonical form. Okay. We'll illustrate this on an equation called the Trichotomy equation, which is uxx plus x uyy is 0. And then to make sure it's elliptic, we impose x being positive. So actually the textbook has the same equation, but with x being negative, and that makes the PDE hyperbolic. Yeah. So if you consider all of R2 as your domain, it's going to be elliptic in half the domain and hyperbolic in the other half. So we're just going to focus on the elliptic half.
What happens when x equals 0? The y-axis.
Well, in that case, actually, it would be parabolic. Yes, right at transition point. Yeah. Okay. So we look at b squared minus ac. So b is 0, a is 1, and c is x. Since x is assumed to be positive, minus x is negative, so it is elliptic. Okay. So now we can jump directly to the ODE that we need to solve. So in this case, A is 1, and B is 0, and C is x. So we need to solve dy dx is plus or minus I times the square root of x for solutions of phi1 and phi2. So what we can do is we can just integrate both sides. So it's relatively easy ODE to solve. So y is plus or minus I, and then x, what's the integral square root of x?
2/3 x to 3/2.
Yeah, 2/3 x to the 3/2. Okay. Plus a constant of integration. So what we can do now is I can stipulate that phi1 and phi2, which are so long as a coordinate curves, phi1 and phi2 equals constant, I can rearrange this. So I can say, for instance, 3/2 y plus or minus I x to the 3/2. So I happen to multiply both sides by 3/2. Not that it was absolutely necessary to do that, but okay. So now I can take the real and imaginary parts of this and call them my xc and eta. So xc is 3/2 y, and eta is x to the 3/2.
Where did the C go? The constant.
That's v1 and v2. So whatever variables you're trying to transform to, that you're treating as constant.
You don't include the actual I with your eta.
No, because when you take real part, imaginary parts, those are
You just
real.
include the.
Yeah.
Okay.
Yeah, what about the I?
Like the A and the B. Okay.
Yes. Okay. So any questions about arriving at this coordinate change?
So in our homework, if we get a problem, we just skip to this part to do
Yeah.
it.
Yes.
So, is that a comma between B of 1 and B of 2? Yeah.
Yeah, because they're both equal because they have plus and
Right.
minus.
I thought that was a product, though. Okay.
Oh, okay. Yeah. You ever a question? Yeah, figure skipping it, I still have a fair amount of work to do.
Skipping the what?
The dy dx part.
But like we don't have to do any of.
Oh, like that stuff over there?
Yeah.
No.
I'm just saying. That.
Yeah, that was
It's
just,
just
yeah,
that-
there. That was
just that-
deriving the equation that you solved.
I'm saying, but like, it takes like that much space.
Even
Yeah.
if we
Just like-
skip to
Yeah.
this part, there's a lot to do. So
Well, the thing, yeah, because, well, in this case, this was a simple ODE to solve, which is not always going to be
Yeah, I
true.
was gonna say.
For,
Yes.
For parabolic, for the for dy over dx, would it equal that without the I?
Oh well, okay. So what happens in this case? In that case, is where you're going to have b squared.
It'll still be b squared minus ac,
Yeah.
though.
Oh, actually, parabolic. This part's gone.
No. Well, I meant hyperbolic. Right?
Yeah, hyperbolic. It's going to be b squared minus ac.
Without the I,
No,
right?
yeah. So in fact, this formula actually is valid for hyperbolic. You just never want to use it. Okay. You have a question? Okay. Oh, doing pretty good on time here. Okay. So then, with these changing variables, we can take partial derivatives with respect to x and y, which actually 2 of those 4 partial derivatives are going to be 0, so that's nice. And you get the transformed PDE. And the thing is, yeah, I'm totally glossing over things here because you have to plug these into the formulas for A bar, B bar, C bar, D bar, E bar, and then F bar and G bar remain the same. So there's still a fair amount of easy calculus and algebra involved in that. It's rather tedious. So what you end up with is, okay. So the original uxx plus xuyy becomes 9/4 times x u c c plus x u eta eta plus 1/3 x to the minus 1/2 u eta, which equals 0. But the thing is, this equation still has your old variables, x and well, actually there's no y in here at least, but there's still an x. Now, eta is x to the 3/2. So what I'm going to do is I'm going to, since all this equals 0 anyway, I'm just going to divide by x. So, okay. So in other words, I'll divide that x by x too. So that's gone, and now I have 1/3 x to the minus 3/2. Now it's much easier to get this into new variables because x to the minus 3/2 is 1 over eta. So my new PE, and actually I factored out 9/4 out of everything, so I can forget about that too. So I have u CXC plus u eta eta plus 1 over 3 eta is 0. So that is my, whoops, I forgot something. Du d eta is 0. So this equation is now in canonical form.
That's 1 over 3 eta, not the C eta, right?
3 eta. Oh,
Just, it was the other way.
oh, okay. As opposed to what?
As opposed to, C is like this.
Oh,
The
no.
3 almost look like, because we've been seeing a lot of,
Oh, yeah.
yes.
Okay. Yeah, like, knowing my handwriting, that
Crap.
could have been a problem. What?
I'm writing half of this equation, half of that one.
Oh, okay. Okay. And actually, this could still be a bit of a pain to solve. Just because of, if it weren't for this term here, this would be relatively easy to solve. We're going to learn all about that when we get to Laplace equation. But for instance, for a general solution, actually it's an equation like this in the first homework where you plug in an exponential and figure out the coefficients. But having this there, especially the variable coefficient of 1 over 3 eta, can also make things a bit difficult. Now, I've actually reached the end of my notes.
No,
But-
So you did 1 over x.
What?
Here, so that's fine.
Yeah, well, because x is positive, so there's no issue
Okay.
there. Okay, so what I'm going to do, I'm going to go out on a limb here and just an approach that I would use to try to solve this. What would it be? And it's an approach we're actually going to learn more about later anyway. Separation of variables. So if we were to do that, if I let u equal some function m of c times another function n, big N of eta. Now, normally this would only be applicable to a constant coefficient problem, which this is not. But I have a hunch that because this one variable coefficient is of a pretty simple form, that it might be workable anyway. Because then u c is m double prime n, u eta eta is m n double prime, and then u eta is m n prime. So if I plug this form into here, you get m double prime n plus m n double prime plus 1 over 3 eta m n prime is 0. And then what you want to do is divide through by mn. So you get m double prime over m plus n double prime over n plus 1 over 3 eta n prime over n is 0. Now, the thing is, with separation of variables, this term here is only a function of xc. This term over here is a function of only eta. Yes,
So you divide it by m and
m and n.
okay.
So, the only way that, well, actually, it's this part, function of only eta. So the only way that that can be is if both of these parts were a constant. So that means that, okay. So for instance, I could say m double prime is equal to some, let's see, yeah. I think how this for ordinary PDEs, unlike the ones that we're going to see later. All right, so if we say that this is equal to some constant, which I'll call lambda, and so n double prime over n is lambda, but for this whole thing to be 0, that means that n double prime plus 1 over 3 eta n prime must be equal to minus lambda n. For both of these to be satisfied simultaneously. So this is equal to a certain constant. This is equal to minus that same constant in order for this to be satisfied. Now, this equation, the first one, is easy enough to solve. If lambda is positive, you get exponentials. If lambda is negative, you get combination of sines and cosines. This is a bit of a taller order because it's a variable coefficient ODE. And actually, I have to confess that off the top of my head, I'm not sure how to solve that. Probably do some sort of change of dependent variable or something. Or maybe it fits some special form. But this is how you can try solving these kinds of equations when you have an elliptic one in canonical form. Because in the hyperbolic and parabolic case, you only have one second derivative term. So a lot of times there's something relatively simple you can do in those cases, like in the parabolic example I gave you. Elliptic is a bit tougher because your canonical form has two second derivative terms. But you can try an approach like this to see if you can get something that you can solve.
Should we write that down?
Why not? But you're going to see a whole lot more of this later.
Okay, then
I mean, what I just said?
that bowl.
Yeah, why not? Well, really? What?
Well, I mean,
We have 7
just
minutes.
kind of like stopped halfway, so I didn't know. Like, is it going to super confuse me later?
No.
Okay.
Yeah, I mean,
Alright.
if anything, all this is going to be reinforced pretty soon when we get to later
I'll write it
chapters.
down.
Okay, fine. Okay, so any questions about what happened here?
The previous one where you have it boxed, is that like what the problem's going to ask us to do? Put it in the canonical form? Or is it
for
going to
most
ask us to
part,
like solve it?
in the homework, there are a couple problems that ask you to solve it, but I think none of those are elliptic.
Okay. Alright.
There's one hyperbolic, number 3 or 4, I think.
Yeah,
Hyperbolic, the first one.
yeah.
So it's going to be one we can solve.
No, we can pretty much solve it.
I should check that.
Be
Yes.
quiet.
Well, you tell me. Okay. Any other questions? Alrighty. Well, actually, now I've really come to the end of my notes. So we'll get into chapter 4, wave equations, starting on Wednesday.